Hello and welcome to this revision session for AQA A-Level Physics Paper 2. So in this revision session what we're going to be doing is looking at answering examination questions for A-Level Physics Paper 2. So if we've been successful and we've learned in today's revision session, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics, and then finally understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? Well, when you complete your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down your working out and answers to the question in the revision session. When you're doing this, make sure you write in full sentences and show your full working out. Whilst in the right hand side, write down any piece of information which you find useful or any hints and tips on answering questions from this revision session. And at the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising for AQA A-Level Physics? Well, the first step is learning the key facts. Use your revision guides, class workbooks, student prep notes and textbooks to learn the key ideas of the course. Now you might want to make mind maps or write out notes yourself to do this. The second step is to test yourself. Use Caboodle, Seneca, a student knowledge checker to quickly test your own knowledge, and you might wish to do this from your own cue cards. Then finally, you want to use examination prep books, homework books, supervised study books, additional workbooks to answer examination questions and mark your own work. And you may wish to even download your past exam papers to do this. So this process of learning the key facts, then testing yourself, then practicing examination questions is the way to prepare for AQA A-Level Physics. So let's have a look at a few questions now on thermal physics. So the first question says, a number of assumptions are made when explaining the behaviour of a gas using the molecular kinetic theory model. State one assumption about the size of the molecules. So pause the video now, then unpause the video when you want to go through your answer. Right, in this type of question it's very important that you know all your assumptions of the molecular kinetic theory model, and also understand what assumptions are due to the molecules, what assumptions are due to the motion of the molecules, and what assumptions are down to the laws of physics that these molecules follow. So what do we know about the size of the molecules? Well, you've got to be aware that the volume of the gas molecules is negligible or much smaller than the volume of the gas itself. So you've got to understand that the molecules have a much smaller volume than the actual volume of the gas in itself. Now it doesn't have a zero volume, it just means that the volume is much smaller or negligible. Now we can also say this, that molecules are point masses, so we would say that we don't really consider their volume. The next question says, figure 1 shows how the pressure changes with volume for a fixed mass of an ideal gas. At A, the temperature of the gas is 27 degrees Celsius. The gas then undergoes two changes, one from A to B and then one from B to C. So firstly, calculate the number of gas molecules trapped in the cylinder using information from the initial situation at A. Then calculate in K the change in temperature of the gas during the compression that occurs between A and B. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, it says calculate the number of gas molecules. So straight away we need to find an equation which has big N in the number of gas molecules. So what we'd say is PV is equal to NKT, where N is the number of gas molecules. You can then rearrange that and you can then make N the subject. You say N equals PV over KT. Now from the situation at A, we know what the temperature is, but we've got to convert it into kelvins by adding 273 to the value in degrees Celsius to get to 300. We know what the number K is, it's just a constant, and then we also know what P and V are because we can look on the graph, and at situation A we can determine the pressure in pascals and the volume in meters cubed. Remember, it's 10 to the minus 3, so when you say it's 0.70, it's 0.70 times 10 to the 3. Multiplying those values together gives you a number of 1.7 times 10 to 22 molecules. As shown on the screen, another way of doing it is to work out the number of moles by doing N equals PV over RT and then multiplying your number of moles by Avogadro's constant, 6.023 times 10 to the 23. The next question is calculate the change in temperature during the compression that occurs. So what you would say is, you would say that in this situation, you know that T over V is going to be a constant. So we can say TB over VB is equal to TA over VA. And what we can know by that point is we know what the V for both A and B are. We know from the previous question what T is, which is, TA, so we can look from the graph, it's going to be 300 Kelvin. So what you can then do is say, well, obviously if TB over VB is equal to TA over VA, well, therefore TB is going to be TA times by VB over VA. Pop your numbers in and you get a value for TB of 214 Kelvin. At that point, it's asking to work out not what the temperature is at B, but rather the change in temperature from A to B. So you know that at A it's 300 and at B it's 214, so therefore our change is going to be 86 Kelvin. The next question says, deduce whether the temperature of the gas changes during the compression from B to C. Then compare the work done on the gas during the change from A to B with that from B to C on figure 1. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first question, how can we answer this particular question on about whether the temperature changes? So what you've got to consider is the idea that if the temperature remained constant, we would say that PC times by VC is equal to PB times by VB, because we know that for an ideal gas, when the temperature is constant, PV is going to be the same value throughout. That is linking into Boyle's law. So what you can therefore say is, therefore, if the temperature is constant, we can say that the pressure at C is equal to PB times by VB over VC. You'll then pop the value in, and then you can work out your answer by doing this 1 times 10 to the 5 times by 0.5 times 10 to the minus 3, their values given from the graph, divided by 0.3 times 10 to the minus 3, also another value given in the graph, to get 1.7 times 10 to the 5 pascals. But the point is the pressure at C therefore is higher than this, so this tells us that the temperature has to be different. So that allows us to conclude that the temperature isn't constant. Another way of doing it would be to work out what PB and P times by V at B is, and also P times by V at C is, and you'll notice that they're not equal, because when you do P times by V at point B, you will get 50, but P times by V at point C is 61, indicating that PV does not remain constant, so therefore T can't stay constant, because PV is only a constant when the temperature is the same. Now the next part is working out the work done on the gas. Now that links into the graph that you've got to the left hand side. Now the work done on a gas can be given by saying work done is P times by the change in V, or thinking about a PV graph, because we're doing P times V to work out our work done, it's going to be the area under the line, because the area under a line is always the y-axis times by the x-axis. So what you would do is you would calculate the area under the graph, but only a part of it, because it's asking for the work done during the change from A to B with that of B to C. So what you would do is you would work out the work done on the gas by looking at the area from A to B. So you work out that rectangular shape underneath the graph from A to B, and then you would also work out B to C, but what you would say is that B to C is the triangle but also the square. Now because there's a rectangular shape for A to B and for B to C, which from the graph they're going to be the same size, they will just cancel out. So therefore the total work done is just the area of the triangle. So you would do a half times by 0.5 times 10 to the minus 3 times by 1 times 10 to the 5 to work out our answer to be about 28 joules. Let's now have a look at a few questions on nuclear physics. So the first question says, explain in terms of binding energy why energy can be released when two nuclei undergo nuclear fusion. Then during the collapse of a supermassive black hole, helium-3 and oxygen-17 fuse to release energy. The equation for this reaction is helium plus oxygen goes to neon. So what we can do, table 2 gives us the date of these nuclei and therefore calculate in joules the energy released when this reaction occurs. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? It's all down to the definition of what binding energy is. So binding energy is going to be the energy that's needed to release all the nucleons from a nucleus. So what we can say is, why is energy released when two nuclei undergo nuclear fusion? Well, it's the idea that the total mass of the nuclei is more than the mass of the fusion product, i.e. when fusion takes place, mass is lost out of the actual system. So this tells us that the binding energy, or more correctly, the binding energy per nucleon increases when a nucleus is formed by a fusion, because therefore the molecule is more stable, so therefore it doesn't need as much energy for the molecules to exist there, so therefore our binding energy will increase. Now in this next question, what have you got to do? You're going to calculate in joules the energy released when this reaction occurs. So what you can remember is we can say E is equal to delta mc squared, where delta m is the change in mass. So the first thing to do is to work out the change in mass in this nuclear fusion process. So work out the mass before, which is the mass of the helium plus the mass of the oxygen, and then find the mass of the neon afterwards and find the difference between the two. We then get our mass to be 0.02272 by finding the difference given with the values in the table. At that point we can therefore turn that into kilograms by doing that value times by 1.661 times 10 to the minus 27 to get our value into kilograms. And by the way, that conversion factor is given to you in the equation book. Then we can say E equals mc squared to then work out our value of E, because C is 3 times 10 to the 8, and therefore we say the answer is about 3.4 times 10 to the minus 12 joules. The next question says, one model of nuclear fusion suggests that fusion happens when nuclei touch. Initially, the helium nucleus and the oxygen nucleus are separated so that the force between them is negligible. They move towards each other until they fuse. Fusion occurs when their centers are separated by a distance of 5.1 times 10 to the minus 15 meters. Figure 10 shows the initial positions and the final positions of the nuclei. Calculate the total change in electrostatic potential energy between the initial positions and the final positions of the nuclei. So pause the video now, then unpause the video when you want to go through your answer. Right, so what's important to note is how you can work out the potential energy from this particular situation. Well, what we know is that in this situation that the potential energy is going to be equal to 1 over 4 pi epsilon 0 times by Q1 Q2 over R. That's the equation from the electrical fields theory that gives us the equation for electrical potential energy. Now we know straight away what Q1 is, because we know that the charge on helium is going to be, helium nucleus is going to be 2, because it has 2 protons, so it's 2 times 1.6 times 10 to the minus 19. Then we multiply by 8 times by 1.6 times 10 to the minus 19, because there are 8 protons in this particular oxygen nucleus. We'll then do over 4 pi times by epsilon 0, 8.85 times 10 to the minus 12, then times by R, which in this instance is the separation between the two nuclei, which is given in the question to be 5.1 times 10 to the minus 15 meters. So we get our answer to be 7.2 times 10 to the minus 13 joules. In questions like fusion and in Rutherford scattering, where you have electrostatic repulsion, it's always useful to be able to understand what the electrical potential energy formula is, so you can work out values based on this particular equation. The next question says helium can undergo fusion reactions with either sulfur or oxygen at the same temperature in a star. The nucleus has properties that depend upon its proton number and its nucleon number. These properties affect the fusion reaction. Discuss for this star how the properties affect the rate of fusion for sulfur and with helium compared to the rate of fusion of oxygen with helium. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this particular question? Well, you've got to think about the charge and how it links to potential energy. So the idea is that doubling the charge will increase the potential energy or force needed to pull the nuclei together. Because if you think about it, it's Q1, Q2 over 4 pi epsilon 0 R. So if we're doubling one of the values of Q, we're going to have to double the potential energy needed. So this tells us that the actual nucleus with the larger charge, which is sulfur, because there's double the number of protons compared to oxygen requires a greater kinetic energy between the particles, or a greater fusion pressure, and therefore that would decrease the rate of fusion. Now, it indicating as well that the larger radius of sulfur compared to oxygen means that the separation can be larger to fusion to take place as well. So therefore the idea would be that the separation can be larger for fusion to take place, so therefore increases the rate of fusion. So you've got to link both those factors in there. Both the amount of kinetic energy needed to overcome the repulsion is thought about, but also about the size of the nucleus themselves. The next question says, a thermal nuclear reactor uses enriched uranium as its fuel. This is the fuel in which the ratio of uranium-235 to uranium-238 has been artificially increased from that found in naturally occurring ore. Describe what happens when neutrons interact with with uranium-235 and uranium-238 nuclei in a thermal nuclear reactor. So pause the video now, then unpause the video when you want to go through your answer. Well, this question is all about memory and knowledge and understanding. It's the idea that when a neutron interacts with uranium-235, it will absorb, the uranium-235 will absorb that neutron, so then the uranium becomes uranium-236 and will then undergo fission, and then will split and give out more neutrons to continue this fission process. Now, remember, the only neutron that can be absorbed by uranium-235 is a slow-moving neutron, or as it's given a name, the thermal neutron, because it's in thermal equilibrium with its surroundings. Whilst when a neutron hits a uranium-238 or interacts with the uranium-238, it will be the uranium-238 absorbs or scatters the neutron and actually becomes plutonium, working it through eventually, so it doesn't carry out fission straight away. The next question says the amounts of uranium-235 and uranium-238 in the ore decrease due to radioactive decay at different rates. A sample of uranium ore today contains 993 grams of uranium-238. The mass of uranium-238 in this sample was greater 2.00 times 10 to the 9 years ago. Show that the mass of uranium-238 in this sample at this time was about 1.4 kilograms. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this particular question? Well, we're looking at how the number of nuclei, or the mass of the radioactive material, has decreased over time. So we've got to use the equation which looks at radioactive decay. So what we'd do is we'd use the equation of n is equal to n0 times by e to the power minus lambda t, where lambda is our decay constant, time is the time in this particular decay, and n0 is the number of radioactive nuclei at the start. So what you do is you pop your values in, because you've got straight away the value of the decay constant, which is 1.5 times 10 to the minus 10. You got the value of t, which is 2.0 times 10 to the 9 from the question, and the question is asking you to work out what the mass is going to be at that particular time. So what you would therefore do is therefore say you can ratio n0 over nt, and therefore you get a value of about 1.36. So that tells us that we're at 993 grams now. So if you convert that to kilograms, so it's 0.993, multiply that by 1.36, my apologies, to get your value to be 1.35 kilograms. Another way of working it out will be to work out the number of half-life that takes place in the particular time period, because we know that the decay constant is 1.54 times 10 to the minus 10 years to the minus 1, so we can work out what our half-life is going to be, or by doing half-life is going to be equal to the decay constant over log 2, so you can work it through like that, and you work out that the number of half-lives is going to be 0.44. So when you work it through like that, because there's only been 0.44 half-lives, you work back to see how much we have at the beginning. So it's going to have 1.36 times more than it does now, so 1.36 times by 0.993 is equal to 1.35 kilograms. The next question says a thermal nuclear reactor requires a minimum of 3% of its uranium mass to be uranium-235. The ratio of uranium-235 to uranium-238 in the ore has changed over time. 2 times 10 to the 9 years ago, the sample contained 52 grams of uranium-235. Deduce whether the sample had enough uranium-235 content to be used in a reactor 2 times 10 to the 9 years ago. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, we've got to find the ratio of this of uranium-235 compared to the total value. So you say the ratio is going to be the number of uranium-235 over the number of uranium-235 plus uranium-238. Now, from the question, we know that uranium-238 is going to be 1,400 grams, because we know in the previous question was 1.4 kilograms. We know that the mass of the uranium-235 is 52. So therefore we can work out our ratio to be what that particular value is. So therefore you'd work it out to be approximately 52 over 1,400. So therefore it's going to be between 3.7 and 3.9%, which is much higher than 3%. So we give our conclusion, we answer the question that's being asked, and we say that yes, it must be able to carry out this fission process because it's above the minimum required percentage of 3%. The next question says, a thermal nuclear reactor uses a moderator to lower the kinetic energy of fast-moving neutrons. Explain why the kinetic energy of neutrons must be reduced in a thermal nuclear reactor. Then, as a result of a collision with an atom of a particular moderator, a neutron loses 63% of its kinetic energy. A neutron has an initial kinetic energy of 2 mega electron volts. Calculate the kinetic energy of the neutron after 5 collisions. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? So what we're talking about is the role of the moderator in the nuclear fission process. So what we say is to increase the probability of the chance of fission, which occurs when a neutron collides with uranium-235. Well, therefore, what we need is we need to have our moderator lower the kinetic energy, so therefore our neutron is a thermal neutron and a much slower moving neutron, and that will allow the neutron to be absorbed by uranium-235. So the moderator reduces the kinetic energy of the of the neutron, so therefore it will be more likely to be accepted by the uranium. Now the next question is asking us to work out the kinetic energy after five collisions. So what you can do is a little bit of a trick. So what we can say is, if we're losing 63% each time, we can say the energy at the end is going to be 1 minus 0.63 times by the energy at the start, or the energy of the incident. Now 1 minus 0.63 is 0.37. So each time you're pretty much saying you're going to be left with 37% of what you started with. So what you can therefore do is, if you want to do this 5 times, you would then get this 0.37 and take it to the power of 5. So what you say is you go, the energy at the end is 0.37 to the power of 5, because there are 5 different collisions, so it happens 5 times, multiplied by the energy at the start. Now the question tells you that the energy at the start is 2 times 10 to the 6 electron volts. Remember, it says 2 mega electron volts, and mega means times 10 to the 6. So we therefore do that times by 0.37 times 10 to the 5, and we get 1.4 times 10 to the 4 eV. The next question says the kinetic energy of a neutron in a thermal nuclear reactor is reduced from about 2 MeV to about 1 eV. Explain why the number of collisions needed to do this depends on the nuclear number of the moderator atoms. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, a link has to be made between the change of kinetic energy of the masses, okay, involved in the collision with that particular momentum. So it's the idea that a nuclear number in the nucleus increases more as the nuclear number increases in the nucleus, more collisions are required to make this take place. So the idea is more kinetic energy is lost when the mass of the moderator is closer to the mass of the neutron. That's because of the idea of the conservation of momentum. So therefore the number of collisions needed increases with the nuclear number, because there's a greater difference between the two values. So when you think about the conservation of momentum, when you have much more different masses, the energy lost out of each collision will be less, so you need them to be of similar sizes. The next question says, one fission process which can occur in a thermal nuclear reactor is represented by the following equation. Calculate in MeV the energy released in this fission process. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you work out the energy release in MeV in this fission process? So the first thing you do is, because you're given the masses in this particular question, you find the mass differences before and after. So you do the mass of the uranium plus the mass of the neutron, then subtract the mass of the xenon, the mass of the strontium, and the mass of the 4 neutrons from that value. So as you can see on the screen, we've worked out the mass before and then subtracted the mass afterwards. That gives us a value of 0.180 U, where a U is an atomic mass unit. So what you can therefore do is take a shortcut and therefore say 1 U, which is a mass unit, times by 931.5 will turn into the value into an energy unit of MeV. That's just a conversion factor, which is a very useful factor to be able to understand and use. So when we do 0.18 times by 931.5, we get 168 MeV, which is the energy released in this fission process, because that's the difference in mass. So the mass of 0.180 U is turned into an energy of 168 MeV. Let's now have a look at a few questions on magnetic fields. So figure 7 shows a search coil positioned on the axis of an electromagnet with the plane of the search coil perpendicular to the axis. A magnetic field is produced by a constant current in the electromagnet. Assume that the magnetic flux density inside the search coil is uniform. The distance between the search coil and the end of the electromagnet is x. Figure X shows how the magnetic flux density B of the field varies with x. So the search coil has 200 turns with a cross-sectional area of 3.5 times 10 to the minus 5 meters squared. The search coil is placed at x equals 0.070 meters. Show that the magnetic flux linkage through the search coil is about 5 times 10 to the minus 4 Webers. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this particular question? Well, the first thing you can do is you can look at the graph, and you can indicate from the graph straight away that the magnetic flux density B at a value of 0.070 meters is equal to about 0.07 Teslas. We can then look at the equation sheet at the back of the book, and we can see that magnetic flux linkage N phi is equal to BAN. So we've got B from the graph, we've got A from the question, and we've got N from the question as well, because N is the number of turns and A is the cross-sectional area. So therefore works out to be about 4.9 times 10 to the minus 4. The next question says the search coil is now moved at a constant speed of 0.80 meters per second along the axis so that x is increasing, and EMF is induced across the terminals of the search coil. Explain what happens to the value of EMF as the search coil moves. Then the search coil passes through the position where x equals 0.10 meters. Deduce whether the EMF can exceed 5 millivolts for values of x greater than 0.10 meters. So pause the video now, then unpause the video when you want to go through your answer. Right, well, the first question, it's all about explaining how EMF is generated. So the point is, as the coil moves, there's a rate of change of magnetic flux linkage through the coil. Now, when you've got a rate of change of flux linkage, that will induce an EMF in that particular conductor. So the induced EMF that's produced is therefore proportional to the rate of change of the flux linkage, which is Faraday's law. So therefore, as the rate of change is going to decrease as it's moving through, that tells us that the EMF produced is going to decrease as well. Now the next question is deduce whether the EMF will exceed 5 millivolts for values of x greater than 0.10 meters. So what we've got to do is we've got to find the change in the magnetic fields, or the magnetic flux, okay, with the distance. So what you would do is that's going to be the gradient of the line, but the issue is this line is a curve. So to find the gradient of this line, you've got to draw a tangent in. So when you draw your tangent in, you can then find your value of what is going to be b over x, and therefore you can use that to therefore work out values of EMF with the idea of EMF is equal to n delta BA over delta t, and work out values this way. So what you can therefore do is, let's say at a value of x equals 0.10 meters, we do b over x and we get 0.095 over 0.137, which is 0.69. Therefore we can substitute this into Faraday's law and work out our value, which should be about 3.8 times 10 to the minus 3 volts, or 3.8 millivolts. The next question looks at gravitational fields. So, the Global Positioning System, GPS, uses satellites to support navigation on Earth. One GPS satellite is in a circular orbit at height h above the surface of the Earth. The Earth has mass m and radius r. Show that the angular speed of omega of the satellite is given by omega is equal to the square root of g m over r plus h all cubed. Then calculate the orbital period of the satellite when h equals 2.02 times 10 to the 7 meters. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, it's the idea that in a satellite in a circular orbit that the centripetal force, which is causing a circular orbit, is going to be equal to the gravitational force, because it's a gravitational force of attraction between the Earth and the satellite which is causing it to go in an orbit. So we can equate the two to each other. So we can say that gmm over r squared, the gravitational force between two objects, Newton's law of gravitation, is equal to mr omega squared. Now, why do we use omega squared here and not mv squared over r? Well, it's because the question wants you to derive it in terms of omega, so it seems sensible to use that particular equation for centripetal force. We then rearrange it and we get our value out to be the one given in the question. The next question says calculate the orbital period of the satellite when h equals that particular value. So what it tells us is we've got the radius of the Earth from the examination equation book, we've got h in the question, we've got g, we've got the mass of the Earth because it's given to us in the equation book, so therefore we can work out omega. So we can work out omega by substituting all those terms into this particular equation, and we get 1.45 times 10 to the minus 4 radians per second. We can therefore say that time period is equal to 2 pi over omega. You need to know that that's just a fact. So therefore 2 pi over the value you just calculated gets you 4.3 times 10 to the 4 seconds. The next question says figure 3 shows the orbital plane of the satellite inclined at an angle to the equator. X, Y and Z are locations on the Earth. X is at the North Pole, Y is on a high mountain and Z is on the equator. The satellite is to be launched from one of the locations. State and explain which launch site, X, Y or Z, minimizes the amount of fuel required to send the satellite into its orbit. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to think about which one are you going to go without the energy being dissipated as it goes up into orbit. Because you've got to think about the amount of fuel required links to how much energy needs to go up in there, so you don't want much dissipated. So what you would do is you'd launch from Z with some speed or some energy. Now the reason why in some speed or some energy argument, in the sense of you can talk about why this is in terms of the energy. So you can say that, oh well, half mv squared is equal to gmm over r, so therefore you can work it through and you can show that actually with Z it's going to be the best place, because if you think about it, it's going to have the largest kinetic energy or the largest initial speed from the Earth's rotation, because at that center it's going to have the greatest amount of kinetic energy from the Earth's rotation. The next question says a satellite has a mass of 1,630 kilograms. Calculate the gravitational potential energy of the satellite when it's in orbit from the previous question. Then a different satellite is in a higher circular orbit. Explain how the linear speed of the satellite compares with the linear speed of the satellite in the previous question. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you've got to work out the gravitational potential energy, and you can work that out by doing G big M small m over r, because to work out the gravitational potential energy you've got to do the gravitational potential G big M over r multiplied by the mass of the actual object moving in the gravitational field. Now you know what big G is, it's a constant given on the equation sheet. You know what the mass of the Earth is, big M, and you know what the mass of the satellite is because it's given in the question. You know what the value of r is, once again because you know the orbital distance from the centre of the Earth, so it's 2.66 times 10 to 7, which allows you to work out a value of minus 2.44 times 10 to the 10 joules. Remember, it's a minus value because all gravitational potential energies when in a field are going to be a minus value. The next question is talking about what happens to the linear speed of the satellite when it's in a higher orbit. Well, what you've got to remember is we can say for orbital speed, a half mv squared is equal to gmm over r. Or you could also say to yourself that the centripetal force is equal to the gravitational force, so it's a half mv squared over r. Half mv squared. It's going to be F equals mv squared over r, which is therefore equal to g big M small m over r squared. So at that point you can rearrange it, and what you can say from this is v is equal to the square root of gm over r. So what it's telling us is, because g and big M are going to be constants, that v is going to be directly proportional to 1 over the square root of r. So when you've got a bigger value of r, because you're in a higher orbit, this is going to give us a smaller value for v. So when you get higher up in the gravitational field, the linear velocity gets smaller. The next question says, Figure 2 shows a moon of mass m in a circular orbit of radius r around a planet of mass m, where small m, the mass of the moon, is much smaller than the mass of the planet, big M. The moon has an orbital period t, and t is related to r by the equation t squared is equal to k r cubed, where k is a constant. So firstly, show that k is equal to 4 pi squared over gm. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, once again, we know that because it's an object undergoing a circular orbit, that the gravitational force gmm over r squared is going to equal the centripetal force mv squared over r, or rm omega squared. So what we can therefore say is we can work out our values and say that, well, if gmm over r squared is equal to mr omega squared, well, therefore by that logic you can say that g big M over R is going to therefore equal omega squared. Now we also know that omega squared is equal to 2 pi over t squared over everything squared, so it'll be 4 pi squared over t squared. Substitute that in, and we can therefore work everything through, and we get our value for t squared to be equal to 4 pi squared over gm all times by r cubed. Now that k is the proportionality constant between t squared and r cubed, so therefore we can equate everything next to r cubed to be equal to k, which is 4 pi squared over gm, as stated in the question. The next question gives us data for 2 of the moons of the planet Uranus. Firstly, calculate the orbital radius x of Umbriel, and then secondly, calculate the mass of Uranus. So pause the video now, then unpause the video when you want to go through your answer. Right, how do you answer this first question? Well, it's important to know that when we're doing this, we can say that t squared is proportional to r cubed. So what we can say is that t squared over r cubed for both of them is going to equal out. So what we can therefore do is rearrange it and make r of Uranus, okay, because which is the question we need, because we're trying to work out the orbital radius there, is going to be equal to the radius of the moon times by tu over tm times by the power of t to the 2 to a third. 2 over 3, or 2/3. Sorry about that. So therefore you pop your values in. So what's the radius of the of m there? So we're going to say that it's going to be 1.2 times 10 to the 8, which is given in the question. What's our value for t for Umbriel? Well, it's given there, it's 4.14 divided by the time period for Miranda, which is 1.41, all to the power of 2/3. You can work out your value to be 2.6 times 10 to the 8. So what, you don't have to change any of the units from days into seconds, because we're just ratioing the values, so you can just keep them in days. Now the next question is calculate the mass of Uranus. Now we've previously in the previous question said that, well, t squared is equal to 4 pi squared over gm times by r cubed. Now what we can therefore do is rearrange this and make big M, because we're trying to work out the mass of Uranus, to be the subject. So we'd say 4 pi squared over t squared g times by r cubed is going to give us a value. Now here, because we do want to get a mass in kilograms, we need to have a time in seconds. So when we're doing this for Miranda, okay, for example, we can work out that the time in seconds for Miranda is going to be 1.41 days. We do 1.41 times by 24, the number of hours in a day, times by 3,600, the number of seconds in an hour, to give us the number of seconds to be 1.22 times 10 to the 5 seconds. We can then substitute all the values in, and we can get our values out to be 8.5 times 10 to the 25 kilograms. The next question says, from the data for the moons of Uranus, deduce which moon in table 3 has the greatest escape velocity for an object on its surface. Assume the effect of Uranus is negligible. So pause the video now, then unpause the video when you want to go through your answer. Right, so what you should do is, you could work out the escape velocities for each object, or you could do a little bit of a mathematical trick to speed the process up. So we can say, to work out escape velocity, we can say that it's going to be the potential energy equals the kinetic energy for our escape velocity, so it's gmm over r is equal to a half mv squared. Now remember, instead of using r, we could maybe use diameter over 2. Why is that? Well, because we're given diameter in the table, so it makes sense to use that. So if we rearrange it and make v the subject, the escape velocity of the subject, we'll rearrange it and see that the escape velocity is equal to 4gm over d all to the power of a half, which is the square root. So therefore we can say v is equal to the square root of 4gm over d. So this tells us that ultimately that the escape velocity is going to depend upon the square root of m over d. So what you can therefore do is, you've got the mass of each of the moons, you've got the value of d for each of the moons, the diameter, and you can just square root each of the terms. So what you would do is you do m over d for each of them and square root them. You then work out quite quickly that that Titania is going to have the highest value for that, so therefore it's going to give the highest escape velocity. The next question says, a spring mechanism can project an object vertically to a maximum height of 1 meter from the surface of the Earth. Determine whether the same mechanism could project the same object vertically to a maximum height greater than 100 meters when placed on the surface of Ariel. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this particular question? Well, it all links into the strength of gravity on each of the planets. So the first thing you can do is, already the strength of gravity on Earth, 9.81, but what's going to be the strength of gravity on Ariel? So we know that G is equal to gm over r squared, where G is a constant and big M is going to be the mass of the object, in this case Ariel, and we know that r squared in this case is going to be the radius of the planet, because we're thinking of the surface of the planet is where it's been projected off, so therefore the separation from the center to the surface is just the radius of the planet, which again is given to you in the question in the table, but you've been given the diameter, so you do diameter over 2. So therefore you can say that G for Ariel, when you work it all through, is 0.25 meters per second squared. Now what we can therefore do is equate the two of mgh on Earth to mgh on Ariel. Now if you notice, m on both sides cancels through because it's the same value, it's the same mass of the object. So therefore we can say GH on Earth is equal to GH on Ariel. So we know the height on Earth is going to be 1.0 meters, because it tells you in the question. We know that the strength of gravity on Earth is 9.8, so therefore we can say 9.8 times by 1 equals 0.25, the gravity on Ariel, times by this height. And when we work it through, height is therefore going to equal 40 meters, so it won't go higher than 100 meters. The next question says, firstly, define the gravitational potential of a point. Then figure 2 shows the positions of equipotential surfaces at different distances from the center of the moon. Firstly, explain how the equipotential surfaces in figure 2 show that the gravitational field is not uniform. So pause the video now, then unpause the video when you want to go through your answer. Right, so the first one is just a definition of gravitational potential, and there are a few key words you've just got to know. It's the work done or the energy required in bringing a 1 kilogram mass or a unit mass from infinity, from outside the field, into a point inside the field. Now, how do you then explain equipotential surfaces in this figure 2 show the gravitational field is not uniform? Well, you can see about the gravitational field strength from the potential difference between the lines, okay, of equipotential in the field. So you can see straight away that the potential differences between the lines is constant, but the distances are not. So this tells us when we do delta V over delta R, what we call the potential gradient, well, that the potential gradient is changing as you're moving through the field. Now, the potential gradient, delta V over delta R, is the gravitational field strength, so therefore it tells us that the gravitational field strength is not going to be constant. You could also link it into the fact by saying the equipotential surfaces are not straight, they're curved. So therefore there's going to be a variance because there's a curvature in the field. The next question says, calculate using figure 2, which was shown previously, the escape velocity at the surface of the moon. And the radius of the moon is 1.74 times 10 to the 6 meters. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, once again, as mentioned, what we do is to work out the escape velocity. We got to say that G big M small m over R is equal to a half mv squared. The potential energy, G mm over R, is equal to the kinetic energy, a half mv squared. That's how we can, that's the condition we have to work out the escape velocity. So therefore we can say the escape velocity, when we rearrange this, is the square root of 2gm over R. Now we've got G because it's a constant. We've got R because we know it's from the surface of the, it's going to be the surface of the particular value there, so you can work it through. So you, in the previous question, you were told what the value, the radius of the moon was, 1.74 times 10 to the 6 meters, so you can pop that in as R. However, we don't have the mass of the moon, so how can you work out the mass of the moon? Well, we can say that the potential is going to be equal to Gm over R, so therefore we can work backwards and say, well, M is equal to minus VR over G. Remember, it's minus because there's got to be a negative potential, because there's a gravitational field which is attractive. So you pop your values in of V, R and G and you get 7.3 times 10 to the 22 kilograms. You pop that into that previous equation and you get 2.3 times 10 to the 3 meters per second. Let's now have a look at a few questions on electrical fields. So, figure 3 shows an arrangement used to investigate the repulsive forces between identical charge conducting spheres. The spheres are suspended by non-conducting thread. Each sphere has a mass of 3.2 times 10 to the minus 3 kilograms and a radius of 20 millimeters. The distance d is 40 millimeters. The capacitance of a sphere of radius r is 4 pi epsilon 0 r. Each sphere is charged by connecting it briefly to the positive terminal of a high voltage supply, the other terminal of which is at 0 volts. After this has been done, the charge on each sphere is 52 nanocoulombs. So calculate the potential of one of the spheres. The charged sphere in figure 3 are in equilibrium. Draw arrows labelled to show the forces on figure 3 on sphere B, then suggest a solution of one problem involved in the measurement of D in figure 3. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, straight away we can say that the capacitance of the object is equal to 4 pi epsilon 0 r. Now we know what r is because we've got the radius of the sphere. It's going to be 0.020 meters because we turned 20 millimeters into meters. So we can say that the capacitance is 2.2 times 10 to the minus 12 farads. Now we know from the definition of capacitance that the capacitance is going to be equal to charge over volts. Okay, so we can rearrange that and say volts or voltage is equal to charge over capacitance. We've got the charge of 52 times 10 to the minus 9 for that particular sphere because it tells you in the question. We then divide that by the charge, which we know to be, sorry, not the charge, the capacitance, my apologies, by 2.22 times 10 to the minus 12 because you just worked that out. So therefore V is equal to 23,000 volts. Now because the charged spheres are at equilibrium, what we can say is that we've got a weight acting from the center vertically down for each them because they've got a mass. Now you've got electrostatic force or repulsion to the right, starting from the inside edge of the sphere for B, because it's being repelled by A because they've got the same charge, so it's pulling away. And then finally, for B, there's a tension label parallel to the thread, and it's going to be upwards because the actual thread itself is taut, so it's pulling up the sphere B with this at the same angle at which the string is. So therefore you need all three arrows to get your marks. Now, one solution to the problem involved in measuring D, which is the distance between the two spheres. Well, what problems could there be? Well, if you've got a conducting metallic instrument, which is like a metal ruler placed between the two spheres, it'll affect the separation because of the movement of charge due to that conductor. So therefore you're going to have to use something like calipers or a ruler, which is made of a non-conductor material. Or you could say that another problem could be that if you physically have the spheres touching each other, or you have touched them and you've taken your measurement, that can alter the reading because the charge has been discharged through you. You could also talk about the difficulty of measuring curved objects. It's difficult to measure the straight line distance between two curved objects. So what you could do is also as well that if you read a ruler behind the spheres, it's going to give you a parallax error. So you've got to think about maybe using a ruler and a set square to line up the ruler with the sphere so you don't get that parallax error. The next question says, show that the magnitude of the electrostatic force on each sphere is about 4 times 10 to the minus 3 newtons. Then a student measures the angle theta when the apparatus in figure 3 is at equilibrium. The student records theta is 7 degrees. Discuss whether this measurement is consistent with the other data in this investigation. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first particular question? Well, what is the force on this object? Well, it's the electrostatic force as given in the question. How do you calculate the electrostatic force? Well, Coulomb's law tells us it's Q1 Q2 over 4 pi epsilon 0 r squared. Now the distance, which is the separation between the two charges, is going to be 80 millimeters. Why is that? Because we go from the center of one charge to the center of the other charge. Now each charge has got a radius of 20 millimeters, so there's 20 millimeters from the center to the edge of the sphere, and also the distance between the two objects themselves is 40 millimeters, so therefore the total distance from center to center is 80 millimeters. So we can use the value of r in this one to be 0.080 meters, because we come from 80 millimeters into meters, and then the charge of both of them is the same. So Q1 Q2 is going to be 52 times 10 to the minus 9 times by 52 times 10 to the minus 9, because we've got it from nanocoulombs into coulombs. So we pop our values through, because 4 pi epsilon 0 is a constant, and we get 3.8 times 10 to the minus 3 newtons. Now the next question says, discuss whether the measurement of theta is 7 degrees is consistent with other data in the investigation. Well, what we know is when each sphere is in equilibrium, we can use our trigonometry to say that, well, tan theta is going to be equal to the electrostatic force divided by the weight. Well, why would that be? Well, if you think about it, okay, when you draw your right angle triangle of forces on the object, you've got the tension, okay, which is acting in the same direction as the string is being taut. You've got the weight acting vertically down, and you've got the electrostatic force acting horizontally in this situation. So when you draw your right angle triangle of forces, you'll realize quite quickly when you draw in theta that in this particular situation the opposite to theta, the opposite to the angle, is going to be the electrostatic force, because that's in the horizontal. We know that the adjacent is going to be in the vertical, which is going to be the weight. So therefore we can say tan theta is equal to opposite over adjacent, so it's going to be equal to electrostatic force over the weight. So it's 3.8 times 10 to the minus 3, the electrostatic force, over the mass of the object, 3.2 times 10 to the minus 3 kilograms, times by the strength of gravity, 9.8. Then we do inverse tan of that, which is 6.9 degrees. So hopefully you've enjoyed this particular revision session on paper 2 for AQA A-level physics. If you've been successful and you've learned in today's revision session, you should be able to answer A-level physics examination style questions, assess your understanding on A-level physics, and understand what topics you need to improve upon for A-level physics. So thank you very much for watching this video on paper 2 revision for AQA A-level physics. based on the 2022 Advanced Information Guidance on what topics will be on the examination. So thank you very much for watching and have a lovely day.